In the long history of human curiosity, few eras have ever radiated as much certainty and triumph as the age of classical physics. It was a time when nature seemed to finally surrender her secrets, when the universe appeared to obey clear, elegant laws that could be written with chalk on a board and tested with the swing of a pendulum. The centuries between the late 17th and 19th centuries built a foundation of confidence so solid that scientists, philosophers, and even poets began to believe that all mysteries were only temporary, that, given enough time, mathematics and logic would decode everything from the motion of the stars to the beating of the human heart. This was the reign of classical physics, a golden period where science wore the crown of certainty and precision, and the human mind felt closer than ever to mastering nature's design. The story truly began with one man who watched an apple fall. Isaac Newton, working in near isolation in the 1660s, developed a vision of the universe that unified heaven and earth under the same laws. Before Newton, people thought the heavens followed divine or mystical patterns beyond human comprehension, while earthly motion obeyed simple cause and effect. But Newton's laws of motion and universal gravitation shattered that divide. The same invisible force that caused the apple to fall to the ground, he claimed, also kept the moon circling Earth and the planets orbiting the sun. Suddenly, the cosmos was not an unreachable mystery. It was a mechanical system governed by predictable forces, measurable, describable, and ultimately, controllable. Newton's equations did more than describe motion. They inspired an entire world view. The idea that the universe was a vast, precise machine governed by immutable laws became the dominant belief of the Enlightenment. If one knew the position and velocity of every particle in the universe at a given moment, one could, in theory, predict every future event. This concept, known later as determinism, was more than science. It was philosophy turned into mathematics. The universe was a clock, its gears turning with perfect precision, and human beings, through intellect and observation, were its master clockmakers. Through Newton's influence, physics became the language of order and clarity. His laws could explain why cannonballs curved through the air, how tides rose and fell, and why comets followed predictable paths across the sky. The mathematical tools he forged allowed scientists to predict eclipses, design bridges, and even navigate oceans with astonishing accuracy. The confidence this gave to civilization cannot be overstated. The natural world, once a realm of divine unpredictability, was becoming a readable text, one that humanity could not only understand but also manipulate for its benefit. As time moved forward, other great minds expanded Newton's framework into every corner of physical reality. Pierre-Simon Laplace, an 18th-century mathematician, famously declared that if an intellect could know all forces and positions of all particles at a single instant, nothing would be uncertain. Both the future and the past would be laid bare before its eyes. That hypothetical being, later called Laplace's demon, symbolized the absolute faith in classical determinism. Every outcome had a cause, every motion followed a calculable rule. The universe was not mysterious, it was mechanical. All that remained was to improve our instruments and sharpen our equations. From the 1700s into the 1800s, this vision of a clockwork cosmos guided nearly every scientific pursuit. Galileo's observations of falling bodies, Kepler's laws of planetary motion, and Hooke's studies of elasticity all folded neatly into Newton's grand system. As mathematics advanced, engineers built machines that mimicked the reliability of nature itself. Steam engines, clocks, telescopes, and navigation systems. With each success, the confidence grew that classical physics was not merely a method of describing nature, but the final truth of how reality functioned. Then came James Clerk Maxwell, who added a new symphony to the mechanical chorus. In the mid-19th century, Maxwell's equations united electricity, magnetism, and light into a single theoretical framework. The idea that light was an electromagnetic wave transformed physics once again. It confirmed that energy, like matter, followed precise mathematical laws. Maxwell's work was so complete, so beautiful, that physicists at the turn of the 20th century often said there was little left to discover. Lord Kelvin even remarked in 1900 that physics was nearly complete, with only two small clouds on the horizon, minor problems that, he believed, would soon be solved. Those clouds, however, would later erupt into storms that would demolish the very foundations of classical thought. But at that moment, classical physics seemed invincible. It had predicted the orbits of planets with unmatched accuracy. It had allowed scientists to understand the behavior of gases, to develop engines that powered factories, and to describe sound, heat, and light in measurable terms. Thermodynamics arose as another jewel in the crown of classical theory, describing how energy moved and transformed. The first and second laws of thermodynamics, conservation of energy and the inevitable increase of entropy, became cornerstones of understanding everything from steam engines to stars. With these principles, humanity built the Industrial Revolution, electrified cities, and mapped the universe with telescopes and mathematics. Precision ruled every discovery. The very idea of scientific uncertainty seemed almost an insult to reason. Yet, beneath this perfection, the seeds of doubt were already sown. The laws that worked so flawlessly for falling apples and orbiting planets began to wobble when applied to the invisible world of atoms and subatomic particles. The smooth, clockwork vision began to creak. But before that breaking point came, classical physics basked in its greatest glory, an age when every phenomenon seemed explainable and every effect traceable to a cause. The world was logical, predictable, and obedient. The language of classical physics carried an almost poetic rhythm, forces, masses, distances, and velocities interacting through elegant equations. F equals ma, Newton's second law, was so simple yet so universal that it applied to everything from a pebble rolling down a hill to a planet spinning through the void. The simplicity was its strength. Where once mysticism had ruled, now mathematics reigned. Every motion could be plotted, every system analyzed. The growing power of mathematical analysis gave humanity a kind of divine confidence, that by calculation alone, one could understand the universe's blueprint. Even outside the sciences, this deterministic philosophy seeped into culture and thought. Economists began to describe human behavior using equations of equilibrium, inspired by Newtonian balance. Philosophers imagined societies as mechanical systems driven by predictable laws of cause and effect. The idea that randomness or uncertainty might have a fundamental role in nature was considered heresy. To doubt classical physics was to doubt reason itself. In classrooms and observatories, scientists and students alike treated the laws of motion as scripture. Experiments confirmed them again and again with astonishing precision. When engineers calculated how long it would take for a bridge to bear a load, their numbers matched reality. When astronomers predicted celestial events, the heavens obeyed. Even the discovery of Neptune was achieved not through observation, but through mathematical prediction, a triumph so perfect it felt like prophecy. With such victories, It's no wonder classical physics was worshipped almost as a philosophy of certainty. The picture it painted of the universe was comforting. Space and time were absolute, immutable backgrounds against which all motion occurred. Objects followed trajectories determined by forces, and those forces could be calculated if one knew the right parameters. There was no mystery left, only detail. Every effect was born of a cause. Every future moment was the inevitable outcome of the present. It was a world without surprises, a cosmos without secrets, or so it seemed. And yet, within this apparent perfection, the first hints of failure flickered faintly at the atomic scale. Atoms were thought to be solid, indivisible spheres, tiny marbles forming all matter. But experiments in chemistry and electricity began to suggest otherwise. The discovery of the electron by J. Thomson in 197 raised questions classical physics could not answer. If atoms contained moving charged particles, how were they stable? According to Maxwell's equations, an accelerating charge should continuously emit radiation, lose energy, and eventually collapse. But clearly, atoms did not collapse. Something was wrong, but the full realization of that failure was still years away. Before that reckoning arrived, classical physics had already cemented its influence on how humanity understood knowledge itself. The success of Newtonian mechanics inspired the belief that reality was fundamentally measurable, that truth was synonymous with precision. Scientists measured with finer instruments, pushing the limits of observation. The discovery of new elements, the development of chemistry, the design of locomotives and telegraphs, all these advances came from the classical mindset that order and predictability were the fabric of the universe. One could argue that classical physics gave birth to the modern world. Without Newton, Maxwell, and their intellectual descendants, there would be no electricity grids, no navigation satellites, no understanding of planetary motion. Every aspect of modern engineering and technology traces its lineage to the era when physics was seen as an exact science of certainty. The atomic bomb, the laser, the microchip, even these later inventions of quantum origin were built upon the mathematical precision first honed by classical thought. Classical physics, in that sense, was not merely a chapter in science. It was the foundation upon which all later revolutions stood. But perhaps the most defining characteristic of this age was its confidence. Scientists truly believed that the universe could be explained completely with the tools they already possessed. In 1871, Lord Kelvin confidently declared that there was nothing new to discover in physics, only finer measurements to be made. The sentiment captured the mood of the entire era, that the grand structure of reality had already been mapped, and that what remained were only details to fill in. It was a remarkable hubris, but also a testament to how successful classical physics had been at describing the visible world. From the orbits of planets to the motion of pendulums, from the pressure of gases to the vibrations of strings, everything seemed to follow laws that were as eternal as geometry itself. And within that predictability, there was beauty, the beauty of certainty, of cause and effect, of a universe that made sense. To those who lived in that era of discovery, it must have felt like standing at the peak of human understanding. The world of classical physics was a world of clarity. Time moved steadily, space stretched endlessly, and motion unfolded with perfect logic. If a planet deviated from its path, the reason was simply a miscalculation or an unseen body exerting force, never the breakdown of natural law itself. Even the heavens bowed to mathematics. The same gravity that pulled an apple down described the dance of galaxies. The same equations that explained a wave in a pond described the movement of light through the ether. It was a unifying vision, and its power lay in its simplicity. But what classical physicists could not yet see was that their success was confined to a particular scale. The human scale, the macroscopic world. The elegant equations that described cannonballs and planets faltered when faced with the behavior of electrons, photons, and atomic nuclei. Yet this failure would not become apparent until the early 20th century. In the meantime, the confidence of classical physics shaped every aspect of science, industry, and thought. The age of precision ruled unchallenged, and it seemed that the dream of a fully knowable universe was at hand. The human imagination was captivated by this mechanical universe. It inspired not only scientists, but also artists and writers. The deterministic vision found its echoes in literature and philosophy, in the orderly progression of time, in the faith that knowledge and reason could illuminate all darkness. To the thinkers of that era, chaos was merely an illusion, and mystery a temporary obstacle. The universe, they believed, was not a labyrinth but a clock, intricate, yes, but decipherable. Yet, as every age of certainty must eventually discover, reality has a way of resisting complete explanation. The cracks in classical thought were faint at first, appearing only in experiments so delicate that they were almost ignored. The ultraviolet catastrophe, the photoelectric effect, and the stability of atoms would soon expose the unseen boundaries of Newton's grand design. But in the age we speak of, the age when classical physics ruled science with confidence and precision, the future still seemed like a continuation of triumph. Humanity believed it stood at the edge of total understanding, unaware that it was instead standing at the threshold of an even deeper mystery. The story of classical physics, then, is not merely one of scientific equations and discoveries. It is a story of human faith, faith in reason, in mathematics, and in the ability of the human mind to comprehend the cosmos. It is a testament to the extraordinary power of logic and observation, but also a reminder that every framework, no matter how perfect, has its limits. The world that classical physics built was magnificent, ordered, and shining with certainty. Yet, in the silence of the atom, a whisper had already begun, that nature's deepest truths might not obey the clean lines of Newton's laws, and that the quest for understanding had only just begun. The supremacy of classical physics did not fade overnight. It was chipped away slowly, almost reluctantly, by the very minds that revered it most. As the 19th century gave way to the 20th, a new generation of scientists inherited the grand machinery of Newton, Maxwell, and Kelvin. They were trained in the certainty of deterministic laws, in the belief that every mystery could be untangled with sharper instruments or longer equations. Yet, when these new investigators turned their gaze toward the atom, they began to sense something unsettling. The elegant mechanical order that ruled the macroscopic world seemed to dissolve into paradox at the microscopic scale. It began innocently enough, with experiments meant to measure light and heat more precisely. Max Planck, in 1900, tried to explain the distribution of radiation from heated bodies. Classical theory predicted that as the wavelength of emitted light became shorter, the energy should rise without bound, a catastrophic explosion of ultraviolet light that simply did not happen in nature. Planck's desperate mathematical adjustment, introducing the idea that energy comes in discrete packets or quanta, was at first merely a trick to fit the data. He did not yet realize that he had placed the first crack in the marble wall of determinism. A few years later, Albert Einstein looked at another puzzle, the photoelectric effect, and used Planck's idea in earnest. He proposed that light itself behaved as if it were made of particles, later called photons. This suggestion defied everything classical physics taught about waves and fields. If light could be both wave and particle, then the tidy categories of Newton and Maxwell were no longer enough. Still, even as these unsettling ideas emerged, many physicists clung to the classical vision, believing that these were temporary inconveniences, not revolutions. At the same time, J. Thomson's discovery of the electron had transformed the atom from an indivisible sphere into a structured system. His plum pudding model imagined tiny negative charges embedded within a positively charged substance. It was a comfortable, almost culinary picture, simple, stable, and classical. But Ernest Rutherford's gold foil experiment in 1911 shattered even that image. By firing alpha particles at thin metal and watching how some rebounded, Rutherford discovered that atoms were mostly empty space, with nearly all their mass concentrated in a tiny nucleus. This was astonishing, yet the new nuclear model posed a fatal contradiction. According to classical electrodynamics, electrons circling a positive nucleus should radiate energy continuously, spiraling inward and collapsing the atom within a blink of time. Since matter obviously persisted, something in the foundations of classical theory had to be wrong. For the first time, scientists confronted a question classical physics could not answer. Why didn't atoms collapse? Why did electrons occupy stable orbits? Why did light from heated gases show bright lines at specific colors instead of a smooth spectrum? Each of these questions struck at the core of the mechanical world. The equations that had guided ships across oceans and predicted eclipses to the second now failed at the scale of the invisible. The more precise the measurements became, the less sense the results made. In 1913, Niels Bohr stepped forward with an audacious proposal. Building on Planck's quantum idea, he suggested that electrons could exist only in certain allowed orbits, jumping between them by emitting or absorbing discrete quanta of energy. The model worked beautifully for hydrogen, explaining its spectral lines with uncanny accuracy, yet it openly violated classical principles. Bohr's atom was stable not because forces balanced, but because nature allowed it to be. It was a rule written not in continuous mathematics, but in quantum leaps, sudden, discontinuous changes that defied the smooth logic of Newton's calculus. Even as Bohr's theory triumphed empirically, many scientists resisted its implications. The classical mindset was not easily surrendered. For generations, the universe had been a grand machine, every motion the result of a measurable force. Now it appeared that, at its deepest level, nature acted in jumps, probabilities, and uncertainties. The human desire for precision met a new frontier. Precision itself seemed to dissolve when observed too closely. Meanwhile, experimental physics pressed forward with zeal. Studies of black, body radiation, spectral lines, and electron behavior accumulated results that no classical formula could accommodate. Each new experiment chipped away at determinism. By the early 1920s, Werner Heisenberg, Erwin Schrödinger, and others began building a radical new framework, quantum mechanics. It replaced certainty with statistical probability, trajectories with wave functions, and predictable paths with the concept of uncertainty. The more scientists understood, the less they could claim to know with absolute precision. To many minds, this shift felt like heresy. For centuries, classical physics had been the language of precision. An object's position and velocity defined its future. An equation could trace its path across time. Now, Heisenberg's uncertainty principle declared that position and momentum could not both be known exactly. Measurement itself changed the thing measured. The observer and the observed were intertwined. The mechanical universe had become a dynamic one, alive with possibility and chance. Yet even as quantum mechanics rose, the shadow of classical physics still loomed large. The success of Newton's and Maxwell's laws in the macroscopic world remained undeniable. Airplanes still flew by aerodynamic equations derived from classical mechanics. Bridges stood by principles of statics. Planetary motion continued to obey gravitational laws to astonishing accuracy. The failure of classical physics was not a collapse of usefulness, but a revelation of boundaries. It was as if the map of the world had been redrawn. The old territories remained correct, but beyond their edges lay unexplored lands where the old compass spun uselessly. The philosophical impact of this transition cannot be overstated. Classical physics had promised a universe of perfect predictability, one in which knowledge equaled control. Quantum theory introduced humility. It forced scientists to accept that reality, at its most fundamental level, might be inherently uncertain. The idea of Laplace's demon, the all-knowing intellect that could predict every future, was banished. No mind, not even in principle, could know all. The failure of classical determinism thus became the birth of a deeper, more nuanced understanding of nature. In retrospect, the grandeur of classical physics lies not only in its success, but in the courage it inspired. The certainty it provided allowed humanity to build civilization's infrastructure, to explore the planets, to trust in the rationality of nature. Even as its limits became clear, its methods, observation, experimentation, mathematical expression, remained the pillars of science. The revolution that followed did not destroy those pillars. It simply built new floors above them. The language of precision still shaped the new physics, but now it carried an awareness of its own boundaries. The electron could no longer be treated as a tiny billiard ball following a defined path. It was a wave of probability. Light could no longer be simply a vibration in the ether. It was a dual entity, both wave and particle. Classical equations still described the everyday world, but deeper within, a different kind of order, statistical, probabilistic, quantum, governed the unseen. As the 20th century unfolded, experiments confirmed the predictions of quantum theory with overwhelming accuracy. The photoelectric effect, atomic spectra, and later, the behavior of semiconductors and lasers all depended on principles that defied classical reasoning. Yet in every triumph of the new physics, the fingerprints of the old remained. Newton's laws still guided spacecraft. Maxwell's equations still ruled radio waves. The universe had not betrayed its old order entirely. It had merely revealed that order to be part of a larger, more complex tapestry. To understand why classical physics failed, the atom is to appreciate the scope of its original triumph. It was never meant to describe the quantum world. It was born from observation of the tangible. Its equations captured motion, momentum, and energy in realms visible to the human eye. When physicists applied those same laws to electrons and nuclei, they asked them to describe a world they were never designed for. The failure was thus not a flaw, but a revelation that nature's machinery is layered, that the logic of the small is different from the logic of the large. Imagine, for a moment, a craftsman who builds perfect clocks. His gears and springs move with exquisite regularity. His pendulums swing in perfect arcs. For decades, his clocks keep flawless time. Then one day, he shrinks his workshop to the scale of atoms, and suddenly his tools behave strangely. The gears vanish into waves, the pendulums blur into probabilities. The same craftsmanship no longer applies because the very fabric of motion has changed. Classical physics was that master craftsman, and the atomic realm was the moment he realized the universe's gears were not gears at all. Still, the legacy of that craftsmanship endures. The language of force, mass, and energy remains central to every branch of science. Quantum theory did not replace classical physics so much as extend it. Just as relativity expanded our understanding of space and time without negating the old truths for everyday speeds, classical laws are still perfectly accurate approximations for the macroscopic world. Only when one descends to the quantum depths does their certainty dissolve into possibility. In this way, the failure of classical physics becomes a story of transformation rather than defeat. The old certainty gave way to a new kind of confidence, one that embraces uncertainty as part of knowledge. The rigid, mechanical universe became a living, dynamic cosmos where probability governs and observation participates. It is poetic, almost ironic, that the era of greatest precision led directly to the discovery of indeterminacy. The pursuit of absolute predictability uncovered the limits of predictability itself. Through that paradox, science matured. Classical physics had taught humanity that nature is knowable. Quantum physics taught that knowledge has boundaries. Together, they formed a more complete picture of existence, one that honors both order and mystery. The universe, it turned out, was not a clock but a symphony, its harmony composed of both rhythm and improvisation. Looking back across the centuries, one can trace the arc of human understanding from Newton's falling apple to the quantum leaps of modern theory. At every stage, the precision of classical physics built the foundation for what followed. Without its clarity, the later revolution would have been impossible. The instruments that revealed the quantum world were themselves products of classical ingenuity. The equations that failed the atom still guide satellites, engines, and architectural marvels. The old physics lives on, not as an error, but as the first language through which humanity spoke to the universe. And so, when we say that classical physics once ruled science with confidence and precision, we are describing more than a historical period. We are recalling a mindset, the belief that reason could pierce every veil, that the cosmos was a masterpiece of mathematical design. It was a faith born not of superstition but of evidence, tested by experiment and crowned by success. That faith was not misplaced. It simply met the frontier of its domain. Beyond that frontier lay another world, stranger and deeper, where certainty gave way to wonder. Today, when physicists probe the quantum realm or explore the curvature of spacetime, they still carry the spirit of that classical age. The quest for precision, the drive to express nature's patterns in numbers, remains unchanged. What has evolved is the understanding that precision does not always mean predictability, that truth can exist even when certainty does not. Classical physics taught us how to measure. Quantum physics taught us how to interpret those measurements. Both are indispensable, both are true within their realms, and together they tell the story of humanity's expanding comprehension of the universe. The grandeur of that first era, the age of Newton, Maxwell, and their heirs, stands as one of the most luminous achievements in human history. It was the moment when knowledge overcame superstition, when mathematics replaced myth, when the heavens were mapped not by gods but by gravity. Its confidence built civilizations, its precision built machines. Even in failure, it gave birth to ideas that would redefine reality itself. Thus, the reign of classical physics did not end, it evolved. Its empire of certainty yielded to a new republic of probability. Its perfect laws transformed into deeper symmetries that govern both atoms and galaxies. What began as a clockwork universe became a quantum cosmos, yet the pulse of order still beats within it. The legacy of that confidence and precision endures in every equation, every experiment, every act of curiosity that seeks to understand the world. In the end, the story of classical physics is the story of humanity's relationship with knowledge, a journey from simplicity to complexity, from certainty to humility, from the predictable to the profound. It reminds us that every discovery carries within it the seed of its own transcendence, and that the pursuit of understanding is endless. The universe may never be fully known, but because of the vision of those who once ruled it with confidence and precision, we continue to reach, to question, and to marvel at the boundless mystery that still awaits beyond the limits of the classical world. For more than 2 centuries, classical physics had stood like an unshakable monument of human reason. Its laws had guided the motion of planets, the fall of stones, the flight of cannonballs, and the hum of machines. To challenge those laws seemed unthinkable. Yet, by the end of the 19th century, a quiet storm was forming in the smallest corners of reality, inside the atom itself. The same atom that had once been considered the indivisible unit of matter was becoming a universe of mysteries, and in its depths, the proud foundations of classical thought began to tremble. The atomic structure did not merely pose questions. It dismantled assumptions that had once defined certainty. The story begins with the ancient dream of simplicity. For centuries, philosophers believed that all matter was built from tiny, unbreakable particles, atoms, a word derived from the Greek atomos, meaning indivisible. It was a beautiful idea, poetic and complete. When modern science revived this concept in the 19th century, it fit neatly within the framework of classical physics. Atoms were imagined as miniature solid spheres, identical building blocks combining in different ways to form the vast diversity of matter. They moved through space according to Newton's laws, obeying predictable forces and collisions, like billiard balls on an invisible table. This image seemed logical, measurable, and satisfyingly mechanical. But the closer scientists looked, the less that picture resembled reality. Chemistry had revealed that atoms of different elements combined in precise proportions, hinting that each type of atom must have its own internal structure. Electricity and magnetism, unified by Maxwell's equations, suggested that the behavior of matter was deeply tied to invisible fields rather than simple contact forces. Experiments with electric discharges in gases soon exposed something smaller than the atom itself, J. Thomson's discovery of the electron in 1897 was the first sign that the supposed indivisible atom could, in fact, be divided. The revelation was electrifying, literally and philosophically. If atoms contained internal charges, then they were not the fundamental units of matter after all. They were systems. Thomson's own attempt to reconcile this discovery with classical theory produced the so-called plum pudding model, in which negatively charged electrons floated within a diffuse, positive sphere. It was an elegant compromise, preserving the overall neutrality of atoms while maintaining the mechanical image that physics demanded. But nature was not so easily satisfied with human simplicity. In 1911, Ernest Rutherford and his collaborators Hans Geiger and Ernest Marston conducted the famous gold foil experiment, firing alpha particles at thin sheets of metal. To their astonishment, while most particles passed through unimpeded, a few bounced back as though hitting something solid. Rutherford compared it to firing a cannonball at a sheet of tissue paper and having it ricochet straight back. The conclusion was undeniable. Most of an atom's mass and positive charge were concentrated in a tiny nucleus, surrounded by vast empty space. The atomic world had suddenly become a landscape of extremes, immense emptiness punctuated by unimaginable density. The model of solid, compact atoms crumbled. And yet, this nuclear structure brought a new, terrifying question. According to classical electrodynamics, electrons orbiting a positive nucleus should behave like tiny charged planets. As they move, they should continuously emit electromagnetic radiation, losing energy, spiraling inward, and collapsing into the nucleus in an instant. If the laws of classical physics held true, atoms could not exist at all. Matter itself should disintegrate. The failure was not minor, it was existential. The search for an answer led scientists into realms that classical logic could not penetrate. Niels Bohr, inspired by Planck's quantum ideas, proposed a daring alternative. He imagined that electrons could occupy only specific orbits, each associated with a discrete energy level. When an electron jumped from one orbit to another, it emitted or absorbed a quantum of light, explaining the strange spectral lines observed in atomic emissions. For the first time, atomic structure began to make sense, but at a price. The continuous mechanics of Newton had to be abandoned in favor of quantized behavior, a kind of staircase where motion occurred in leaps rather than flows. This concept defied every intuition nurtured by centuries of physics. The atom was no longer a miniature solar system governed by gravity, like forces. It was a stage for quantum drama, where rules changed from one level to the next. The simplicity of classical orbits was replaced by the mysterious mathematics of probability. The atom's structure was no longer mechanical, but abstract, its components both waves and particles, its boundaries defined by uncertainty. For those steeped in the certainty of classical thought, this was more than scientific shift. It was an intellectual earthquake. The very notion of causality, the bedrock of physics, began to blur. In classical systems, knowing a particle's position and velocity meant knowing its future. Inside the atom, such precision was impossible. The more accurately scientists measured one quantity, the more uncertain the other became. The idea that nature itself might be indeterminate was almost unbearable to minds trained in the deterministic tradition of Newton and Maxwell. Yet the experimental evidence grew undeniable. The discrete spectral lines of hydrogen, the stability of atomic structures, the peculiar behaviors of electrons, all pointed toward a deeper reality governed not by continuous laws, but by quanta, by packets of energy that obeyed their own mysterious arithmetic. The atom had revealed itself to be both particle and wave, both localized and delocalized. The tidy boundaries of classical understanding had dissolved. The challenge was not just technical, but philosophical. If the atom defied the old laws, then those laws were not universal after all. The foundations of science, once thought eternal, had become conditional, valid only within certain limits. The mechanical picture of the universe was incomplete. Space and time, once absolute, became contextual. Forces became interactions mediated by fields and probabilities. The atomic structure had not simply added a new detail to physics, it had rewritten its language. In this shifting landscape, the atom became both the destroyer and the savior of physics. By exposing the limits of classical reasoning, it forced the birth of a new science, quantum mechanics. The revolution that followed would reshape everything: chemistry, electronics, even cosmology. But in these early years of discovery, confusion reigned. Scientists stood between two worlds, one ruled by determinism and precision, the other by uncertainty and chance. The atom had become a paradox, a universe within a grain of existence, whispering that the familiar laws of motion were only shadows of a deeper truth. The transformation was as much emotional as intellectual. Imagine a generation of thinkers who had grown up believing that the universe was a clock, its ticking predictable, its gears eternal. Now they faced a cosmos that flickered and shimmered with unpredictability. The atom, once a symbol of solidity and permanence, had revealed itself to be mostly empty space, its parts in constant, unknowable motion. The matter that made up stars, stones, and human bodies was not fixed at all, but dynamic, uncertain, and alive with quantum motion. And so, as scientists peered deeper into the heart of matter, they were forced to confront the fragility of their own understanding. The discovery of atomic structure was not just a scientific milestone. It was a mirror held up to the human quest for certainty. It showed that the laws we create are only approximations of truth, that each new layer of knowledge opens another, more mysterious one beneath. The atom did not simply challenge the foundations of classical physics. It redefined what a foundation meant. It taught humanity that even the most unshakable structures could tremble when confronted by the unknown, and that every certainty carries within it the seed of its own transformation. The deeper the investigation went, the more the atom seemed to mock the certainty that had once ruled physics. What had begun as a simple mechanical image was dissolving into an invisible dance of energies. When Ernest Rutherford's model introduced the dense nucleus, it explained the deflection of alpha particles, yet it raised an even darker mystery. What held those positive charges together? By every known rule of electrostatics, the nucleus should explode from its own repulsion. The forces required to bind it exceeded anything classical physics could imagine. A new kind of glue, unknown, unseen, and far stronger than electromagnetic attraction, had to exist within the heart of matter. That invisible force would later be called the strong nuclear interaction. But at the time, its existence was only guessed at. Nature, it seemed, guarded her most intimate secrets behind paradox. The nucleus was tiny, yet contained nearly all the atom's mass. Electrons swarmed around it, yet no one could explain how or why they stayed in place. Scientists built instruments to look deeper, only to find that looking changed what they sought to see. The classical notion of an independent, measurable reality began to erode. Measurement itself became a participant in the drama of the atom. As these puzzles multiplied, the old equations of Newton and Maxwell were stretched to their limits. They had been written for predictable systems, not for realms where observation altered outcome and probability ruled motion. It was Werner Heisenberg, working in the mid-1920s, who finally confronted this breakdown head-on. He threw away the idea of visualizing electrons as miniature planets and replaced them with abstract quantities matrices that encoded only what could be observed. His mathematics made accurate predictions, but it described no familiar picture. To many of his contemporaries, it felt like abandoning reality itself. Then came Erwin Schrödinger, who sought to restore a more tangible image. He imagined the electron not as a particle darting around a nucleus, but as a wave spread through space, described by a simple yet mysterious equation. That wave was not a physical ripple like those on water, but a probability field, an invisible pattern describing where the electron might be found. The atom, under this vision, was no longer a miniature solar system, but a resonant structure, a standing wave of potentiality. The bright lines in atomic spectra were the musical notes of that resonance, each corresponding to a quantized energy state. With these insights, the old walls of classical physics collapsed completely. The atom had transformed from a solid unit of matter into a shimmering cloud of mathematical probability. And with that transformation came the realization that the world was not built from certainty, but from possibility. When an electron was observed, it appeared in one place. When unobserved, it existed everywhere its wave function allowed. The boundary between existence and non-existence blurred into probability itself. Such a picture would have seemed impossible to Newton, yet it explained experiments with astonishing accuracy. Even as quantum mechanics triumphed, resistance remained. Albert Einstein, one of the fathers of the revolution, was deeply uneasy. God does not play dice with the universe, he famously declared, refusing to accept that chance was woven into the fabric of nature. He believed there must be hidden variables, unknown causes, restoring classical determinism beneath quantum uncertainty. But every attempt to find them failed. The atom seemed to obey laws of its own, untraceable to the deterministic order that had guided physics for centuries. The implications spread far beyond the laboratory. If matter itself was uncertain, then so was everything built from it: stars, stones, and even consciousness. The classical dream of complete prediction gave way to a universe of probabilities, where knowing the future meant knowing only likelihoods, not certainties. Yet paradoxically, this uncertainty did not weaken science. It strengthened it. By accepting probability as a fundamental feature of nature, physicists could now describe the behavior of matter with precision far beyond anything classical laws had achieved. The failure of the old model became the success of the new. Inside the atom, reality proved to be layered and dynamic. The nucleus was discovered to contain protons and neutrons, themselves composed of smaller entities, quarks, held together by gluons, carriers of the strong force that defied classical intuition. Surrounding them, electrons occupied quantized shells, their arrangements determining the chemistry of every element. The shapes of these electron clouds explained why atoms bonded, why metals conducted electricity, and why light interacted with matter the way it did. Each revelation exposed not chaos, but a deeper order, an order classical physics could never have foreseen. From this revolution grew technologies that would define the modern age. Transistors, lasers, nuclear power, and computers all trace their origins to the quantum understanding of the atom. Every piece of modern electronics operates by manipulating electrons, whose behavior classical theory declared impossible. The atom had not only challenged the foundations of physics, it had rewritten the foundation of civilization itself. Yet, amid this triumph, a quiet humility emerged. Physicists now recognized that every model, no matter how successful, is only a map, useful within certain boundaries, but never the territory itself. Classical physics remains perfect for planets, pendulums, and projectiles. Quantum physics reigns within atoms and subatomic realms. The two coexist, each valid in its domain, each incomplete without the other. The atom had taught humanity that knowledge is layered, that truth unfolds in scales. In the centuries before this realization, the atom had been the dream of simplicity. After it, the atom became the emblem of complexity. Its discovery transformed not just physics, but philosophy. It forced thinkers to abandon the idea of an objective reality untouched by observation. It revealed that nature's laws are not always intuitive, that even the smallest entities defy the human urge for solidity and certainty. The classical world was built on predictability, the atomic world thrived on mystery. Still, the challenge of the atom was not destruction, but evolution. Classical physics had built the staircase. Quantum physics climbed it. Each failure of the old theory opened a doorway to new understanding. In this sense, the atom was both the end and the beginning, a paradoxical core of matter that simultaneously broke the rules and redefined them. As scientists explored further, they found that even the nucleus was not the ultimate boundary. Particles appeared and vanished, energies converted into matter and back again, echoing Einstein's great equation E equals mc2, E equals mc2, E equals mc2. The distinction between substance and energy, once clear in classical thought, dissolved completely. The atom, once imagined as the smallest solid piece of reality, became a theater of transformation where mass and energy exchanged roles. The foundation of the old world was now fluid, dynamic, and interconnected. Looking back, it is astonishing to realize how much the concept of the atom reshaped the human world. It dethroned the mechanical cosmos and replaced it with one of probability, symmetry, and uncertainty. The certainty that had powered the Industrial Revolution yielded to a subtler understanding, one that accepted imperfection, chance, and duality as part of truth. The atom taught humanity that reality is not a fixed machine, but a process of constant emergence. And yet, in this uncertainty, there was beauty. The mathematical patterns describing atomic behavior, wave functions, quantum numbers, symmetry groups, revealed a hidden elegance deeper than any clockwork. The universe, once envisioned as a rigid mechanism, now appeared as a living tapestry, woven from both order and spontaneity. The atom was no longer merely the building block of matter. It was a symbol of mystery and potential, proof that knowledge evolves and that even the smallest particle holds infinite depth. Thus, when we say the atomic structure challenged the foundations of classical physics, we are describing a moment when human understanding pivoted from certainty to curiosity, from control to wonder. The atom broke the boundaries of the old universe and invited us into a new one, a universe that humbles and inspires in equal measure. Within its invisible heart lies the greatest paradox of all, that by shattering the walls of certainty, it gave science a wider horizon, one vast enough to hold both the predictable and the possible, both the mechanical and the miraculous. The mystery of atomic stability became one of the greatest puzzles that classical physics could not solve. According to the laws known at the time, an atom, as imagined by early scientists, simply should not exist. If electrons were tiny charged particles orbiting a positively charged nucleus, then by the principles of electromagnetism, they would constantly lose energy as radiation. Like a planet spiraling toward the sun, each electron should collapse into the nucleus in a blink of an eye. Yet atoms clearly endure, forming the matter of the universe with unshakable stability. Something in the classical picture was deeply wrong. This paradox haunted physicists at the turn of the 20th century. They could calculate exactly how fast an electron should radiate energy, and every equation predicted disaster. The atom, if classical laws were true, would vanish instantly, but reality stubbornly disagreed. The contradiction was so severe that it threatened the entire foundation of physics. It meant that the equations that explained planets and pendulums could not explain the structure of the very matter that composed them. Then came Niels Bohr, a young physicist with a daring idea. In 1913, he proposed that electrons did not move freely as classical theory suggested, but occupied fixed orbits, each corresponding to a specific energy level. In these orbits, electrons did not radiate energy. Only when they jumped between levels did they emit or absorb light. It was a radical departure from all previous understanding, but it worked. The spectral lines of hydrogen, once an unsolved riddle, matched Bohr's predictions perfectly. For the first time, stability had an explanation not through classical motion, but through quantum restriction. Yet even Bohr's model was only a step. Later discoveries revealed that electrons do not orbit at all, but exist as standing waves surrounding the nucleus. Their stability arises from resonance, from the way waves reinforce themselves only in particular patterns, just as a plucked string vibrates at specific notes. The atom endures not because its parts move like machinery, but because they form a harmony of probability. The failure of classical physics to explain stability thus opened the path to quantum mechanics, where energy is not continuous but quantized, and where matter itself is a song written in discrete tones. This realization changed everything. The solid world is built not from certainty, but from balance between forces that classical physics could not imagine, between attraction and motion, between wave and particle, between chance and order. The stable atom is the quiet miracle that defied classical logic and revealed a deeper truth. Nature protects its building blocks not through mechanical predictability, but through the elegant laws of the quantum realm, where stability is born from the rhythm of the unseen. The mystery of radiation became the turning point where classical physics began to crumble. When scientists studied how atoms emitted and absorbed light, they found behaviors that defied every established rule. Classical theory claimed that energy should flow smoothly and continuously, like water from a tap. Yet experiments showed that atoms released energy in sudden bursts, tiny packets of light known later as quanta. No equation from Newton or Maxwell could explain this strange, step-like emission. It was as if the atom refused to play by the continuous logic of the visible world. The puzzle deepened with the study of blackbody radiation, where heated objects glowed at specific colors depending on temperature. Classical physics predicted that as the wavelength shortened, the energy emitted should rise without limit, leading to what was mockingly called the ultraviolet catastrophe. But the catastrophe never happened. Nature behaved differently. In 1900, Max Planck, struggling to make sense of this, proposed a desperate solution. Energy could only be emitted or absorbed in discrete amounts, proportional to its frequency. This was not a comfortable idea. It violated centuries of belief in continuity. But it worked. Planck's constant, a small but profound number, became the key to unlocking the atomic world. A few years later, Einstein took Planck's concept further. He suggested that light itself was made of quanta photons, with energy bundles that explained the photoelectric effect, where light striking metal ejected electrons only if its frequency was high enough. Classical waves of light could not account for that threshold behavior, but quantum light could. This was a revelation. Radiation was not a smooth wave, but a granular flow of energy packets. The very nature of light, so long believed to be a continuous wave, was dual, behaving as both particle and wave depending on how it was observed. When these discoveries met the mysteries of the atom, the old framework collapsed completely. Electrons jumping between energy levels produced the sharp spectral lines that classical models could never predict. The atom radiated not in a continuous glow, but in discrete flashes, each representing a quantum leap. It was as if nature herself was quantized, revealing her energy in coded steps rather than a flowing stream. The old picture of smooth, mechanical cause and effect gave way to a new one ruled by probability, resonance, and transition. This failure of classical physics was not a defeat but a transformation. It revealed that the universe, at its most fundamental level, is digital rather than analog, governed by distinct units of energy and matter. Radiation was no longer a byproduct of motion. It was a fundamental expression of how particles and waves exchange energy. The atom, once a miniature machine, became a vibrant field of transitions, where light and matter danced to quantized rhythms. In the glow of that realization, the limitations of classical physics became clear, and from its ashes rose the dawn of quantum theory, reshaping humanity's understanding of energy, light, and the hidden pulse of the universe. The experiment that shattered the classical vision of the atom came from a simple idea and a sheet of gold foil. At the dawn of the 20th century, scientists believed they already understood the atom's structure. According to J. Thomson's plum pudding model, atoms were spheres of positive charge with negatively charged electrons scattered inside, like raisins in a pudding. The positive and negative charges balanced each other perfectly, and the atom appeared as a smooth, featureless entity. Everything about this picture fit comfortably within classical physics. There was no reason to doubt it, until Ernest Rutherford decided to test it. Rutherford and his students, Hans Geiger and Ernest Marston, directed a stream of alpha particles, tiny, fast, moving projectiles emitted from radioactive elements toward an ultra-thin sheet of gold foil. According to Thomson's model, the particles should have passed straight through with only slight deflection, since the atom was thought to be a soft, evenly distributed cloud of charge. But what the scientists observed was shocking. Most particles did indeed pass through, yet some were deflected sharply, and a few even bounced straight back. It was as if, Rutherford said, you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. This single observation demolished the entire classical picture of the atom. If alpha particles could rebound, there had to be something extremely dense and positively charged inside the atom, something capable of repelling them with tremendous force. The only logical conclusion was that nearly all the atom's mass and positive charge were concentrated in a tiny central core. Thus, the nuclear model of the atom was born. The vast empty space within the atom, revealed by this discovery, was an idea so alien that even Rutherford hesitated before accepting it. The solid matter of the world was not solid at all. It was mostly emptiness, held together by invisible forces. The implications of this discovery rippled across science. The old plum pudding atom was gone, replaced by a planetary model where electrons orbited a dense nucleus much like planets around the sun. But this new model immediately faced a deadly problem under classical laws. If electrons were moving in circular orbits, they should continuously emit radiation and lose energy, spiraling into the nucleus in a fraction of a second. The atom should collapse, yet it didn't. The Rutherford model explained the nucleus, but failed to explain stability. Classical physics had been unmasked once again. It could describe motion and force, but not permanence. The gold foil experiment had not just changed atomic theory. It had forced a philosophical reckoning. The atom was no longer a miniature version of the solar system governed by predictable motion. It was an arena of intense energy, where forces and fields shaped matter in ways unseen and unimaginable to classical thought. The revelation of the nucleus was both a triumph and a warning. Nature, at its smallest scales, did not obey human expectations. What made Rutherford's work so monumental was not just what he discovered, but how it changed the very method of science. Observation had overthrown authority. For centuries, theory had guided experiment, but now A simple observation had rewritten the theory itself. The universe revealed its structure not through imagination, but through evidence, and that evidence refused to fit the comfortable patterns of the past. In the wake of Rutherford's discovery, new questions multiplied. What held the positively charged protons together inside the nucleus? What stopped the electrons from crashing inward? Why did atoms emit light in distinct colors? Each of these mysteries exposed another fracture in the classical world. It was clear that something deeper was at work, something beyond continuous forces and mechanical motion. The atom was no longer a passive object. It was a dynamic system where energy, charge, and motion existed in delicate equilibrium. Rutherford's gold foil experiment stands as one of the most dramatic turning points in the history of science. In its simplicity lay its power, a beam of particles, a sheet of gold, and the collapse of centuries of belief. It transformed the atom from a theoretical curiosity into a structured universe of its own, with a dense heart surrounded by the mysterious dance of electrons. That revelation would pave the way for Bohr, Heisenberg, Schrödinger, and all the pioneers of quantum physics who followed. In the soft glow of a laboratory in Manchester, the atomic age began, not with explosions or machines, but with the quiet deflection of invisible particles. The gold foil experiment revealed that matter is not what it seems. It is space and energy bound by laws beyond sight. The atom, once thought simple and indivisible, became a vast landscape of discovery. And through the shock of that realization, classical physics reached its limit, opening the door to a new vision of reality, one where mystery, not certainty, became the foundation of truth. The dawn of quantum ideas marked the moment when science stepped beyond the shattered walls of classical physics. Once the old models had failed to explain atomic behavior, a new framework had to emerge, one that could make sense of the invisible and unpredictable world within the atom. It began quietly, with Max Planck's desperate attempt to solve the problem of blackbody radiation, but it soon grew into a revolution that would redefine the meaning of reality itself. Planck's proposal that energy comes in discrete packets, or quanta, was not just a mathematical trick. It was the seed of a new understanding. When Albert Einstein expanded this concept to explain the photoelectric effect, he revealed that light could act as both a wave and a particle, something unthinkable in classical physics. This duality, where light sometimes behaved like a ripple and other times like a bullet, challenged every assumption about the nature of energy. Matter, too, would follow the same strange rule. Louis de Broglie suggested that particles like electrons also had wave-like properties, meaning that the boundaries between matter and radiation were not as firm as once believed. The atom was no longer a miniature mechanical system. It was a field of probabilities, where energy, position, and motion blurred into one continuous mystery. Then came Niels Bohr, who combined these ideas into a model that offered both structure and logic to the chaos. He proposed that electrons existed in fixed energy levels around the nucleus, jumping between them when absorbing or emitting light. These jumps explained the sharp lines in atomic spectra that classical physics had failed to decode. Though simple, Bohr's theory captured the essence of quantization. It showed that energy in the atom was not continuous but stepped, organized by hidden rules that gave matter its stability. The true revolution, however, arrived with Werner Heisenberg and Erwin Schrödinger. Heisenberg discarded visual imagery entirely, replacing orbits and particles with mathematical relationships that described only what could be measured. Schrödinger offered another vision, the atom as a wave system, where electrons existed not as point particles, but as smear, doubt clouds of probability. Together, these views formed the foundation of quantum mechanics. It was a new kind of physics, one that did not demand certainty but embraced ambiguity, describing nature not as fixed but as potential. The atomic world, once a puzzle, became a living map of possibilities. Observation itself became part of the process, and the simple act of measuring could alter the outcome. Classical physics had sought to define what is, but quantum physics taught humanity to understand what could be. It replaced absolute predictability with statistical truth, and in doing so, it captured the essence of reality at its most fundamental level. From these quantum ideas arose technologies that transformed civilization: transistors, lasers, atomic clocks, computers, and even the principles that guide nuclear energy. The revolution of atomic science was not just a shift in equations, it was a shift in philosophy. It taught humankind that the universe is not a machine, but a mystery unfolding in patterns of probability, where certainty dissolves and wonder begins. The collapse of classical physics in the face of atomic discovery was not an end, but a beginning, a transformation that gave birth to modern science as we know it. When the old laws failed to explain the stability of atoms, the behavior of electrons, and the discrete nature of radiation, physicists realized that the universe was far stranger and more intricate than they had ever imagined. The fall of certainty became the rise of imagination. Out of the ruins of predictability emerged quantum theory, relativity, and an entirely new way of seeing reality, one rooted not in absolute laws, but in probabilities, interactions, and energy fields that shape the very essence of matter. In this new world, the atom was no longer a miniature solar system of solid particles, but a dynamic pattern of possibilities. Every electron existed not as a definite point, but as a cloud of potential locations, collapsing into reality only when observed. The classical dream of a perfectly measurable universe dissolved into one where uncertainty was not a flaw, but a fundamental principle. Werner Heisenberg's uncertainty principle captured this new truth. The more precisely one measures a particle's position, the less precisely its momentum can be known. The universe, it seemed, had built mystery into its design. This radical shift gave science new power. By accepting uncertainty, physicists could now calculate with astonishing accuracy the behavior of atoms, molecules, and even subatomic particles. The mathematics of quantum mechanics, though abstract, described reality more precisely than any previous theory. It predicted chemical reactions, explained the colors of stars, and revealed why matter is stable. What classical physics saw as failure, quantum physics turned into triumph. The boundaries of understanding expanded beyond the visible world, allowing scientists to peer into realms of unimaginable smallness and energy. From this transformation grew the technologies that define modern life. Every computer chip, laser, smartphone, and satellite owes its existence to the understanding born from classical physics collapse. Nuclear energy, medical imaging, and quantum computing all trace their lineage to this revolution. What was once a theoretical correction to an old problem became the foundation of the modern technological age. The failure of classical physics did not destroy science, it liberated it. Yet beyond technology, the deeper impact was philosophical. The new physics taught humanity humility. It showed that even the most elegant theories can crumble before new evidence, and that knowledge is a living process, not a fixed monument. The universe revealed itself as both lawful and unpredictable, structured yet flexible, precise yet uncertain. It became clear that truth in science is not about final answers, but about evolving understanding. In this way, the failure of classical physics became the most creative moment in human thought. By accepting the unknown, scientists learned to see beyond it. The revolution of atomic science was not just a scientific event, but a turning point in human consciousness, a reminder that the universe is larger, subtler, and more astonishing than our oldest certainties could ever contain.